All right, frames of reference. A frame of reference is a coordinate system relative to which motion can be observed and described. Kind of a vague statement, I suppose, um, but really that's basically it. It just means it's any um, person or object, and relative to that, you're going to take measurements or consider the situation, right? So it could be, well, there's a picture of a bus down here, right? So you could look at a person on a moving bus and you could use that frame of reference, right? You could take measurements and do any calculations relative to that person, right? Basically pretending you're that person. Note that the person doesn't have to be moving at a constant velocity. They don't have to be at rest. Um, it could be, any of these situations. However, if you want an inertial frame of reference, right? That is a special frame in that it has no net force acting on it, therefore it moves at a constant velocity. That is possibly v equals zero. Sorry, it always does that. But that's just one possibility, right? So for an inertial frame is not necessarily a frame that is at rest. It's just a frame that's moving with a constant velocity. And you can always take the perspective if you are a person in that, or you're thinking of it as a person in that reference frame. You can always say they are at rest, and everybody and anything else is moving relative to you. In fact, that's probably the easiest way to do any calculations, right? So, for example, a man standing on the ground watching a bus go by is an inertial frame, or that individual standing on the ground watching the bus, if this is the fella here, he's in an inertial reference frame, right? He's standing still, he's watching the bus go by. But also, if the bus is moving at a constant velocity, then it is an inertial reference frame. And one way to tell that, I think I just wrote that a little bit here, is if you set a ball on the floor, it will not move, right? If you're on the bus and it's going with a constant velocity, then you could set a ball down on the floor and it's not going to roll anywhere, right? You're in an inertial frame. A non-inertial frame then is just an accelerating frame, right? With respect to some other, but usually like that means there's some net force on it, so you're going to feel it. Right? So, for example, the bus slowing down is a non-inertial reference frame. And if you were on the bus, if you had your eyes closed or you weren't able to look at the windows, right, you would still feel the net force on you. You'd feel like, oh wow, feel like I'm trying to, be pushed forward or something. And in this case, you would know that also if you had a ball lying on the floor, right? It would roll forward. Another concept that's going to matter for today and going forward is this idea of a fictitious force, right? So fictitious, just as it sounds, means it's not real, right? A fictitious force is an apparent but non-existent force invented to explain the motion of objects within accelerating, i.e., non-inertial frames of reference, right? For example, a person sitting on a bus might come up with a forward force to explain the ball's motion, right? And the acceleration they feel. So if you go back to that example, somebody sitting on the bus here, they set their ball down on the floor. It's not going anywhere. Then all of a sudden, the ball starts rolling forward and they feel a bit of a force forward. So they might, if they had never experienced this before in their life, they're not looking out the windows or seeing anything that's going on. They might just say, oh, there's a forward force all of a sudden that exists. And I don't know what's happening, so I'll just call it that and I'll say that's a thing. But it's not a real force, right? It just exists because they're in a non inertial frame. Okay. Let's look at an example here. After a disagreement on a plane, a woman opens the cargo door and drops her girlfriend's luggage. The plane's ground speed is 200 meters per second, so that means the speed relative to the ground, right? So it's moving through the air with that speed. Um, we're ignoring any wind speed, so let's just assume air really doesn't matter here. Determine the velocity of the luggage when it hits the ground 300 meters below from the woman on the plane's perspective, and then B, an observer on the ground's perspective. Right? So if we look at part A, we've got an airplane traveling. Let's see if I can somewhat sketch an airplane. And let's see, we look something like that. All right, so we've got our airplane here, and somewhere inside here, we've got the woman dropping the luggage. And what happens here? We've got the luggage that's going to fall down and hit the ground. Now, have we drawn this correctly? So, yeah, I've drawn it absolutely from the perspective of this woman on the plane. And a way that you might think about this or maybe manipulate this situation mentally is forget about the ground, right? Suppose it's like pitch black, dark out. You can't see the ground at all, right? You're on this plane, and we're ignoring any air friction or anything like that. So you're standing here in the, near the bottom of the plane. You open a cargo door and you just drop, right, the luggage, right? You just drop it straight down. And let's even for simplicity, suppose that this luggage has a light on it, right? Or maybe you just drop a light. I don't know. But from your perspective, when you drop this, right, what do you see? What does it look like? Right? And it looks like the light just goes straight down, right? Because you have in the plane or in the airplane, you have a velocity, which I guess is 200 meters per second forward. But that's also the velocity or the x component or horizontal component of the luggage's velocity, right? It doesn't lose that. There's no force when the luggage drops. Sure, it also has this, right? Vx, let's call it, equals 200. And that doesn't change. There's no force acting on it in the x direction. Potentially some air friction when we're going that fast. But again, we're ignoring that. So if you were standing there in the plane, that's all you would see is just this, luggage going straight down. And that's kind of more generally, like I said, a real part of answering questions like this or doing problems like this is really getting yourself in the perspective of the person here. What do they see? What do they not see? If it helps, like just sort of black everything out like I did there and just, really imagine what it would be like. So for this, we can define, let's say, that can be the positive x, although for this one, it doesn't really matter. And let's define down as positive. Now, this distance here is going to be 300 meters. So this just becomes basically a kinematics problem here, right? In the y direction, right, we've got v1 equals 0. And I guess I could say right, v1 equals 0. We want to figure out the velocity of the luggage, right? So we want v2 when it hits the ground. We know the acceleration, and it's positive because I said down is positive, and we know the distance is 300 meters. So I guess I could put in. So that's really, we just have to pick which equation we want. I guess that would be v2 squared equals v1 squared plus 2ad. And that means v2 squared equals 0 squared. So this doesn't even really matter. That's just 0. 2 times 9.8 times 300. And that means v2 equals the square root of all that. I guess 2 times that is 19.6. And that means V2 equals 76.7 meters per second. And this down is a real key to this too, right? Because that's their perspective. It's just going straight down, and that's the speed it hits the ground. Okay, so that's someone on the plane's perspective, or rather from their frame of reference, right? That's what they see. And this is a perfectly valid thing to say that right, that's the speed that it hits the ground with from someone in that frame of reference. Right? Now, it may matter more to look at the frame of reference of someone on the ground since it hits the ground, which is in a different reference frame. So if we look at that, it's a very similar problem if we look at part B, which is from someone on the ground. In this case, though, when the luggage is dropped, and let me just sort of half sketch this out. Here's our ground. So the luggage is dropped. And in this case, though, it does have, right, it does have V1, which equals the same velocity as the airplane. So it starts out with just a horizontal component to its velocity, and V1y equals 0. So that means when it hits the ground, right, we'll say V2x will equal 200 meters per second because the x component of the velocity never changes. There's no force on it in the horizontal direction. And V2y, we just calculated, right? 76.7 meters per second, because just like when we were doing these problems before, we can look at each direction completely independently, right? So we would look at what happens in the y direction by just taking gravity into account and doing the same calculation we just did up here above. And that means to figure out the total velocity, we can put these two together and we can say, I'll just do a little sketch of it here. So I'll say this is V2. I'm assuming is going to look something like this. And we know this component here is 200 and this component here is 76.7. That means V2, remember, magnitude of V2, we get just using Pythagoras, which is 200 squared plus 76.7 squared. And when we work that out, we get 214.2. And to get the angle, I'll make the angle right here, like that. So that means that the, I don't know, a lot of space there. Tangent of theta is 76.7 divided by 200. And if I take the inverse tangent of that, I get 21 degrees. Therefore, V2 is 214.2 meters per second. And I'll just report that as 21 degrees below the horizontal. And this is because I don't. I'm given a direction above, or am I? Nope. So that again, but it doesn't really matter because this wouldn't be like a northeast, southwest type of thing. This is right below the horizontal. It's got a somewhat downward component. So interestingly, not a lot of downward velocity yet compared to the horizontal component, just because that was pretty significant for it to start. Right. So apparent weight can be considered a fictitious force, right? In other words, you're in an elevator that's accelerating either up or down. For me, I guess it's a little easier to think about it like I'm going up, and for that, while it's accelerating, right? Once it's moving at a constant velocity, your weight, as it were, is exactly the same as it is if it's not moving, generally speaking. But while you're accelerating, right, you've been in an elevator, you feel heavier while it's accelerating up. And so that apparent weight you could look at as some fictitious force, like I have this extra weight or whatever, which is, again, really just because you're in an accelerating frame of reference. Right? Um, so I'm just looking at an example for this. A 70-kilogram person is on an elevator accelerating 2 meters per second up. They throw a 20-kilogram medicine ball upward, accelerating it at 8 meters per second squared. Determine the apparent weight acting on the person. So we've added a little bit to this question. All right, so all I did here is sketch. I'm just going to say why the positive y direction is up. It doesn't really matter. And I know the acceleration is 2 meters per second. Right, that's the acceleration of the elevator and the person. Okay, so this little free body diagram right here, let's just let that be the person. And it seems like there's a lot going on here, right? The elevator is accelerating up. The person's throwing a medicine ball. Um, okay, but let's just look at it from the perspective of the person, right? And let's look at what are all the forces on them, right? And so we say, well, we know there's going to be the force of gravity down. Okay. Let me go a little bigger. There's going to be the normal force up, right? That's just the force of the ground on the person. And the person is throwing a medicine ball, right? So we can go to Newton's third law, right? That is, whatever force the person is exerting on the medicine ball to throw it up, the medicine ball also exerts on them, pushing them down. And if you wanted to do an experiment like this, you don't even need to be in an elevator. Just hold on to something that's got a little bit of weight so you can tell. Try to hold it really still and stand on a scale. And then as you're pushing it up, right, as you're accelerating that object up, you're applying a force up. It will apply an equal and opposite force down, and you'll actually see your mass on the scale increase while you're pushing it up. So I'll just write this here. Let's say this is the applied force, or this is the force of the ball, the medicine ball. And we can also look at the ball over here. So here's my little medicine ball, and we'll look at this. It's got the force of gravity pulling it down, and it's got the applied force on it. I guess you could call this the applied force on the medicine ball, and this is the force of B on the person, could be the other force over there. So if we look at this, right, so we look at just a medicine ball, right, what's going on with this, and we sum all the forces in the y direction. We say, well, there's this applied force pushing it up, and there's gravity pulling it down, and that all has to equal mg. And I believe we're told that this medicine ball is 20 kilograms. So the applied force, which again we don't know, minus the force of gravity on this ball, so it's 20 kilogram ball times 9.8 equals the mass of the, oh, that's a big difference here. It all equals ma, the actual acceleration of the ball, which we're told is 8 in the up direction, and that also means this one here, the 9.8, would be negative, but I've already subtracted the whole term. Otherwise, technically, I would add it and I could put that acceleration as negative, and it all works out. Anyway, if I do add 196 to both sides after I do that multiplication, I get that the force on the ball is 356 newtons. Right? So that's the force that this person is applying to the ball to accelerate it up at 8 meters per second, overcoming the force of gravity on it. And since that's the force of A on B, or the person on the ball, that means that's going to be the exact same force on the person. Now we can do a similar analysis on the person. We can sum all the forces in the y direction, and that is going to equal the mass of the person times by their acceleration, which might be different. So we've got the normal force in the up direction, which we don't know. But that is their apparent weight. And we've got the force of the ball on them, or force of B on A, which we just calculated, minus the force of gravity on the person, all has to equal MA for them. So the normal force we don't know. The force of the ball on the person is 356 down. And the force of gravity on this person, well, they're 70 kilograms. So we multiply that by 9.8, and that has to equal their mass times their acceleration, which is 2 meters per second squared up, which we said is positive. That means the normal force is 1182 newtons when we work that out. So we could look at this then, and we could say, well, how does that compare to their normal weight, right? So compare no acceleration, right? Then and their mass is 70. So if we do that calculation, we get 686 newtons. Right. So that's their weight, if you will, when they're not accelerating and not throwing a ball up, right? But right now they're feeling a force, a normal force from the ground pushing up at them, which is sort of your experience of weight. So we could look at their apparent weight, which often we use R, which in this case we just take what they're experiencing, divide by what it would normally would be, and we get 1.76 G. Right? So you could say right now they're experiencing it's not, that's a 2. They're experiencing 1.72 Gs. And the whole idea here with representing this as G is just saying relative to, so for this person, this amount here represents 1 G, right? One amount of force applied to them from gravity when they're not accelerating anywhere on Earth. So usually, often this is something like sometimes with rides or things like that, but or with pilots, you'll often hear like talk of like how many Gs they're experiencing because of how they're accelerating, and that's just relative to what 1 G of force would be. So it gives you some sense of like what your apparent weight would be. In their cases with pilots, they sometimes get up to like 9, 10 Gs. That is like 9 or 10 times the force of gravity would be on them, which is an extreme amount of force.